Hi everyone, Mr. Lee here. In this video, we are going to cover our final topic for momentum, and that is going to be 2D momentum. Okay, so the way that I want to approach this is I want to first start off with the conceptual idea behind 2D momentum, and then I want to dive into how we can solve it mathematically. Alright, so let's begin. So 2D momentum is a lot like 1D momentum, where the concepts still remain the same. For elastic collisions, we have energy is conserved and momentum is conserved. Well, momentum is conserved for all of the situation, but this right here, momentum being conserved, that's the most important part about the conservation momentum unit itself. All right, now with the elastic collision, I'll give you a scenario here. So for a elastic collision, let's say that we have a red ball, and this red ball is moving, let's say, down and to the right, and it will collide with a blue ball. Okay, and this blue ball is just, let's say, it's just moving straight to the left. Okay, so post collision, no matter what happens, we can say that the momentum initial for the system is equal to the momentum final for the system. So let's try to think about how all of this will go through. Okay, so if we take a look at this red ball is moving both down and to the right. However, this blue ball is just going straight to the left. So if we're thinking about this conceptually, the total momentum is most likely going down. And that's because this leftward momentum and, this rightward momentum from the red ball and this leftward momentum from the blue ball, they have a high chance of canceling out depending on the individual momentum of the objects themselves. So what I mean by that is, let's say that, so we know that momentum is mass times velocity. Let's say this red ball has either a great mass or a great velocity. So either one of those is pretty big compared to the blue ball. That means this red momentum is going to be pretty big. So that means that if the red ball's momentum is overall pretty big, after they collide, this down and rightward momentum is most likely going to stick around. Now let's reverse that. Let's say that the momentum of the blue ball is pretty big, right? We have a great big momentum of the blue ball, so it could either be the mass that's big or the velocity that's big compared to the red ball, or maybe even both. So after the collision, the important thing here is that after the collision, the momentum of the system will most likely will resemble the momentum of the blue ball if the blue ball had a majority of the momentum. So let's just uncover what the post collision might look like. So we have a leftward momentum and a rightward momentum, and let's just assume that both of these momentums are about the same. Okay, for the red and the blue. So if the momentum for the red and the blue are about the same, post collision, we can say that the red ball will most likely be bouncing to the left. Okay, and because nothing's going to be affecting the downward motion, it can also move down as well. So post collision, the red ball will be most likely moving down and to the left. And let's have the blue ball right here. So post collision, if we have the blue ball right there, the leftward momentum is mostly likely going to be canceled out by this rightward momentum, and it's going to bounce off. And so we can say that it will be going to the right mostly. So what we're looking at here, so this rightward momentum is the final momentum of the blue ball, and this down and left is the final momentum of the red ball. So if I'm looking at this scenario as a whole, the overall momentum is still downwards because this leftward momentum from the red ball and this rightward momentum from the blue ball, they're most likely cancel out, leaving only this downward momentum of the red ball. Okay, so momentum is conserved. Much like initially, this red ball was moving down and to the left. So, down and to the right, and this blue ball was moving to the left, so this rightward momentum of the blue ball would most likely be canceled out by the leftward momentum of the blue ball, leaving only the downward momentum most likely going down. Okay, so we can say that the momentum is conserved. Now we did all of that very conceptually, and we can apply this conceptual knowledge. It really helps before we even do the math, because now we can predict what we're looking for. So let's do the same scenario, except this time I'm going to redraw it real quick. We'll say that the red ball is pretty tiny. Okay, pretty tiny momentum. So pretty tiny momentum. It's not moving fast. It's not big at all, but it is moving down and to the left. Okay, compared to the blue ball. Let's say the blue ball is not only is it pretty massive, but it's also, you know, it's chugging along. It's got a pretty big velocity. So, and we'll have it moving to the left. And so what we can say here is that this red ball has both a down and right momentum, and this blue ball only has a leftward momentum. Now, post-collision, because this blue ball has the majority of the momentum of the system, we can say overall the post-collision is going to resemble this blue ball collision. Now before we do that, let's identify what our initial momentum is going to be looking like. So the majority of the momentum is coming from this blue ball, so we can say that the majority of the momentum will be going to the left. But this red ball also is providing a tiny amount of downward momentum. Now notice what I did there. So what I did was I separated the x and the y momentum, because you can't add the x and the y vectors. And so if this is our overall momentum, we can say that initially the overall momentum will be left and downwards. So I'll write that down, left and downwards. But because the momentum of the blue ball is so big, I'm going to say it's going to be majority to the left. So if I were to draw a vector arrow showing the size, I would just do something like this. Okay. Now, post-collision, we want to resemble this idea that the most of the momentum will be left and downwards. Okay. And so what we can say here is that this, let's draw the red ball and let's draw the blue ball. Right? Post-collision, what's going to happen is chances are this red ball is going to move up a little bit. Okay, it's gonna have that upward deflection, and this blue ball will have a slight downward deflection. Now, the reason why I say it's a slight downward deflection is because it has a lot of inertia. It's not going to be knocked around by a lot, but because we know that momentum is both mass times velocity, because the mass of the blue ball is very big in magnitude compared to the mass of the red ball, the momentum of this downward motion of the blue ball will be greater. The momentum of the downward will be greater compared to the red ball. Okay. All right. So here we have left and downward. So far we know that the final momentum has to be left and downward, right? So it has to be both. So we have the downward covered. Check. So what we can also say is that the because this red ball is pretty tiny, after it collides into this big blue ball, this red ball will have a huge reflection or deflection to the left, right? It's going to be, it's going to shoot over. It's like, imagine like a linebacker or like a sumo wrestler running into like a 5-year-old child, right? The 5-year-old child is just going to go flying backwards. And this blue ball will also have a momentum going to the left. It might even have it going to the right. I don't know. But what the important thing here is that the overall momentum of the system matches the initial momentum of the system. Okay, so that's a big idea here. So that's how you can approach it conceptually. So this is a elastic collision. If we were to take a look at a explosion type of problem, let's do an explosion type of problem before we do a inelastic problem, because as you know, explosions and inelastic are just the same but in reverse. So let's say we have a cannonball. Right? And we know that this, let's do a watermelon. We know that this watermelon will break off into 2 pieces. Okay, so this watermelon is moving to the right, and for whatever reason, it explodes. All right, and we have piece 1 going up and to the right. Okay, and we have piece 2 going like this. This will be down and to the right. Okay, so this is what we know. We got to think about this conceptually. Initially, the momentum of the system is to the right. So that must mean that the final momentum of the system must also only be to the right. Now see what I do here. I'm going to do all my x momentum in blue. I'm going to make it a little bit bigger for us to see. So this momentum, if this is my vector, and this right here, boom, Okay, that's my x momentum. I don't know what that numerical value is, but it's there. And here we have my x momentum for ball 2. So what this means is that we can add both of these x momentum together. So I'm going to say P1x, and this is going to be P2x. Now, there's a very specific reason why I am labeling those, so you should also label them as well. Now I'm going to do the y momentum in red. So we have this upward momentum. I'm going to call this P1y. And we have this downward momentum. We can call this P2y. Okay, so this is currently our scenario, right? We have this watermelon. It was flying to the right, but it exploded for whatever reason, and we get something that ends up like this. So it's important to know that both of these are right angles right there. Okay, so we know that the overall momentum, it has to be conserved. So that means that the initial momentum was to the right, and the final momentum has to be to the right. So that must mean that there are no vertical momentum. And this is the reason why. We can say that the initial x momentum was to the right, okay, because there's no vertical momentum here. Therefore, the final x momentum must also be to the right, okay. We can also say that the initial y momentum is 0. Therefore, our final y momentum must also be 0. Now, this is a big idea right here. This is a highlighted idea. This y momentum. Now, momentum has positives and negatives, and that's where this comes into play. So if we take a look here, we can see that object 1 is moving upwards and to the right, and object 2 is moving downwards and to the right. So what we can say, if we know that the total sum of the y momentum must equal 0, and we know that it's P1y plus P2y, we can say that the y momentum, P1y, is equal to P2y. And we can say that because this upward magnitude will have to cancel out this downward magnitude in terms of momentum. And we know that it does because this downward momentum, it's a negative value, and this positive momentum, this upward momentum is a positive value. But the important thing is that the vertical momentum are equal. And that's only because initially the object was only moving to the left. That's the key idea there. We can only say that the vertical momentum here is canceled out because initially it was only moving to in the x-axis. Okay, so if I were to create a formula for the x momentum, it would look something like this. P sub x is equal to, let's see, the final momentum is equal to the initial momentum, final x, there we go. Okay, so the final x momentum is equal to the initial x momentum. And we know that the final x momentum is equal to P1y plus P2y. So that must mean that if we were to add both of these momenta, I'm going to highlight it so that you can see what I'm talking about, this P1x and this P2x, if we were to add up those two values, the momentum would equal to the initial momentum of the system. The y momentum doesn't do anything. It's only the x momentum that actually matters. Okay? All right. And so that's an explosion. We could also do the reverse for a inelastic collision. Oh, speaking of, so here we can say that momentum is conserved. Okay? Big idea. I wanna say this every single time because it's important and will come up. The momentum of the system is conserved. However, the energy for the system is not conserved. Okay, I'm going to say this after every single time because that is the big idea behind this entire unit, basically. All right, now let's do a inelastic problem. So for an inelastic problem, it's going to look just like the explosion one. And so let's do a blue ball, right? So this is like clay, and then we have this red ball. So we have blue clay and this red clay. This red clay is moving up and to the right. And we can say that this blue clay is moving down and to the left. Now, I want to add like an extra conceptual layer here. Let's say that the momentum of the blue initial is greater than momentum of the red initial. Okay, so the momentum of the blue initial is greater than the momentum of the red initial. Now, the reason why I'm doing that is because now we can actually predict after the two combine what is going to be the direction of the combined material. All right, so if we know that the momentum of blue is greater than the momentum of red, that must mean that the overall momentum is going to resemble the momentum of the blue. And so without using any numbers, right, because we're just doing conceptual here, I'm going to have the red and the blue combined. We can say that this final momentum is going to most likely resemble the momentum of the blue, with a giant little asterisk. And that asterisk is, we know that both of these objects here have a horizontal x momentum. Okay, and I'm gonna draw that in here. So this one has a initial in the x to the right, and this has a initial y downwards. And we know that this red one has the initial x to the right, and this has a initial y upwards. And so if we're looking at the arrowheads here, what is adding to each other? And the momentum that is adding to each other, I'm going to highlight it, hopefully you can answer it by now, is the initial x's. So that must mean that after they combine, the combined system, or the combined object, is going to have a greater momentum going to the right, because the two momentum are going to add up to each other. So the momentum is going to increase going to the right. Okay, and if we were to compare the momentum vertical, we notice that here that the arrowheads, okay, one is going down, one is going up, they're going to cancel out. Well, not 100%, but there's a higher chance that the momentum of the blue will nullify the momentum of the red. And so what we can do to predict the motion of the combined masses is that we know it will most 100% be going to the right, and it's going to move downwards. But I'm going to write downwards just a tiny little font there, only to emphasize that the y momentum have canceled out just a little bit. Right? And so if I were to draw my vector, it would look something like this, down and to the left. Now, in terms of the equation, what we can do is we can say that, let's do over here, we can say that the momentum of the system, right, P momentum system, let's say for the x direction, is going to be, so the initial momentum will be POX plus POX of the blue, and then POX of the red. So initial momentum of the blue plus the initial momentum of the red is equal to the overall x momentum, and that will be both the initial momentum and the final momentum of the system. Oops, that should be an equal sign, excuse me. So it should be both. So I'm going to highlight that. So based on our scenario, this is what our equation will look like. Now for the y one, we can create a similar equation. We can say that the total momentum of the y, which is the momentum initial, which is the momentum final of the y, okay, because momentum has to be conserved. So that's what this line is just saying. Initial momentum y is equal to final momentum y, that's just momentum is conserved, is equal to the initial momentum of the y plus of the red plus the initial momentum of the y blue. Now the reason why I'm having it as a addition is because technically we're adding the momentum. It just so happens to be that the blue momentum, when you put in the actual equation with numbers, that'll be negative. Okay, and then this will be our equation for the y momentum. And then we can combine it at the end. All right. So the final step, in order to find the axis, or excuse me, the x and the y momenta, I just want to do a quick run through. Nothing new that we haven't seen before. So let's use a blue ball. So if we know that this blue ball, is moving to, let's say, up and to the right, and the problem gives you that this is the angle theta, right? So this is the overall momentum. We can say, so this right here, excuse me, I should use dotted lines, and that's because it's a component. So this can be px, and this can be py, and this is theta, right? So we can say that px, because this this component, this vector, is adjacent to that theta, that will be p cosine of theta, and that is just the hypotenuse times the trig function. Okay, and here this will be p sine of theta, and it's sine because it's opposite of that angle. All right, so in all these situations, we didn't actually use sines and cosines, but that's how we would just break it down. We would create the vectors, right? And then you would have like the tiny little thetas there. And then you should be able to figure out the actual momenta using the trig functions. All right, that's that. This is the 2D momentum video. This actually puts a nice little bow on our entire unit. This is like the next level, the next step. But the important ideas is that momentum is always conserved, okay, for the system, no matter what. Energy is conserved only for elastic collisions, and it is not conserved for inelastic or explosions. Keep that in mind. We also went over how to create net momenta formula. Okay, and the important idea there is that the initial momentum and the final momentum are always going to be equal to each other. All right, this was Mr. Lee, and that is it for momentum. I'll see you next time. Bye-bye.